Okay. So, okay. So can you hear me?
Yes.
Yes.
Okay. So I just say a little bit. So then, so last Monday, I think is not very fast. It's the first time, and most time is for the review purpose. But last Wednesday, I think the lecture is so fast. So today or maybe later, I will try to do it in a slow-paced way. So otherwise, you can just read the book, right? So so I will try just to use the iPad. I will just write the notes by hand while giving the lecture. So if you have questions, you can ask. So I hope this might be a little bit faster than Euro lecture, but definitely slower than Monday's lecture. Last Wednesday's lecture. So it might be easier to understand. If you don't understand, you can see the video. You can see the video later. Okay. I'm not sure, right? So is everything going good with all of you, right? So if you have difficulty in finishing the homework, maybe homework is easy. Maybe the difficult part is reading the textbook or follow the lecture. So I mean, if you have difficulty, you can let me know. I'm not sure how many courses you are taking because somehow this is a difficult time. You might find hard to finish the coursework, right? So if you have some concern, you can just say now. You can unmute yourself and just let everybody else know, right? So we can figure out the best way to do the next month of this course, right? Okay. Yeah, you can just say. You can just say. You can just unmute yourself and say, "Is there some problem?" Or you can email me later. Okay. So this is a plan, right? So I will tell you again of my plan for this course. So we don't have many lectures, but we need to cover like several lectures on Markov chain, right? This week we will cover Markov chain. Maybe one more lecture for next Monday. So then we probably spend 1 or 2 lectures on ergodic theory, or we just skip them if we spend too much time on Markov chains. But Brownian motion are the basic objects in probability, right? It's the basic objects. So it's the basic continuous in time object is the very basic one. We must cover that, and we must spend a lot of time on Brownian motion. And if we have time, we might talk about a little bit on equal calculus stochastic differential equations. This actually are very useful. But yeah, so another thing I want to talk to you is like how to do the evaluation in the end, right? I guess all of you, like, except maybe 2 students never show up and never do the homework, but most of you for the homework side are very good. But for last midterm, maybe not that very good, right? And it's very likely we won't have final exam. So because if some people even expect the stay at home will stay, right? We continue like I don't know when, right? So maybe it will become serious in a couple of weeks. So definitely this semester we cannot go back to campus. So there are 2 possible ways, right? Either I give you like several take home, of course it's take home exam, you just submit the final exam to me, right? Another way is like I mean, if you do very well, right, for midterm and or homework, I know you, right? You ask questions, I know you are good, right? So probably you can just get A. I don't need to do more evaluation. But otherwise, maybe so if we don't have homework, right, don't have take-home exam, maybe I just schedule with some of you, maybe 10 of you, or 10 to 15 of you, to do some like interview type evaluation. You don't need to really prepare a lot, right? So I just see, right, just ask you basic questions or concepts, right? So you can even find some reference, right, during the oral exam, right? Yeah, it will be last for like 10 minutes or 15 minutes, right? It will be very fast. So this is the only way, like, to make you learn even in this very difficult time. But so you need to worry a lot, right? Because most of you, right, so will get A or A minus. So you probably get the email from the graduate school. So you can choose pass or fail for this course, maybe before April something. You can choose pass or fail. So if you choose that, as long as you do reasonable amount of job, except for 2 students who never showed up, so you probably don't need to worry about fail, right? You will definitely pass. But if you feel confident, right, you will A or A minus, you don't need to change to that. But it's all up to you. It's all up to you. Okay. So any questions now? If you have some concern or questions, you can let me know. Or you can email me. Okay. Okay. I will just start today's lecture. Right. So it seems okay. So I will just start. So any questions? If you have questions, just unmute yourself and start to talk. Okay. So otherwise, I will start. So last lecture really fast, right? So we should go back a little bit. So if we spend some time on reading the book, it should be fine. But anyway, let's first let me okay. Okay. So this is my my notes. Okay, so just to give me 1 second, I need to have some water. Okay. Okay, so let's start. So last time, I will just make several remarks on, so for last Wednesday's lectures. I write an announcement for you, so you can find the announcement. There's a link, right? This is also a link for MIT Open Courseware. It's on applied probability. so you can follow the link to 3 lectures on Markov chains. So, but those are all on finite state Markov chain, but it's very intuitive. You can basically just follow, you will, yeah, I'm very sure all the students in this class can follow the lectures very easily. It's very intuitive and it gives you examples, right? It's definitely go to, I mean, if you want to do a review on Markov chains with finite state space, right? The state space is finite. So let's say from 1 to m. It's very good course. And the instructor speaks I mean, very fluent English. I mean, he never repeat, right? So it's like he exactly follow the line. So, so it's very amazing. Okay, you can follow the video there to do a review. So our course is more advanced course. So I will still follow so our textbook. So because somehow you need to do in a rigorous way, or you need to do proof, right? So so we must go through this technicality, right? Okay, so let's start by briefly reviewing what we did in last lecture. So let's say, so we are considering a Markov chain. We're considering Markov chain. So on the space S. So those space is has a sigma field, right? So this can be a sigma field. So sigma field of S. So let's assume, right? If we assume S is countable, if we assume S is countable, right? So for instance, S can be or the natural number, right? Or S can be some ZD, right? ZD. So the D-dimensional lattice, right? ZD, something like this. Right? Okay. Okay. So what is the Markov property, right? So Markov property actually is Markov property is a very useful property. So when we do modeling, right, this is a so what is a Markov property? Right? Markov property basically tells us. So let's say you have a state. So this is your state and position m. So let's still using this. So this is a state and position and time n. Right? This is a state and time n. And you want to compute you want to predict the future, right? So let's say the future is xn plus 1, right? It's n plus 1 time. So you want to compute, you can predict the future. So you want to compute the transition probability, let's say from I to J, from I to J. So the Markov property basically says, right, your history doesn't matter, right? So you might have a different trajectory, right, to reach xn, right? You might have many trajectory. You might have different background or history before you reach xn, right? But as long as you reach xn, from I, right, to possible future state, right, it doesn't depend on the history. It doesn't depend on those history. This is exactly what stated in the Markov property or assumptions. So in the definition of Markov chain, right? So you see, right? So this is one, this is a one. Yeah, so this is one possible history or trajectory, right? And it doesn't really matter about zeta, right? It only matters about the I. So the position I, right? So this is called Markov property, right? It's kind of memory-less property. It's kind of memory-less property, and also it's kind of it's also kind of some like so conditional independence, but it's a very vague way, right? So in last week's homework, right, there's an exercise, right? If you condition on xn, so the future event, so and the past event, right? The past event, the future, right? This is the past. So they are kind of conditional independent. But this is just a vague way, right, to say that. Right? So this is called Markov property. So I find a very good example in Scott Sheffield slides. I will show you these slides a little bit, right? So you can better understand the Markov property, I mean, intuitive way. Okay, so let me find his let me find his slides. Okay. Okay. So let me share screen. This. Okay. So I mean, this is a funny example, right? So does relationship status have the Markov property, right? I mean, so the answer is no, right? I mean, so it's very easy to believe the answer is no, right? So let's say this is a relationship status, right? So in a relationship, right, single, right, is complicated, married, or engaged. So why this is not a Markov process, right? So they have several states, right? They have transition probability, of course, right? But you can believe, right? You can believe. So let's say if you are engaged, right? If you are in a state engaged, so probably, right? Yeah. So the history. So the history actually matters, right? So what the how do you reach the status engaged? Maybe will influence the probability get married, right? So definitely this is not a Markov process. It's not a Markov chain. So yeah, so this can help you understand the basic property in some way. So there's a very important example, right, in mechanics, right, in Newton's dynamics, right. So I will write share screen. Okay. So I will write. So I mean, let's open. Let's add one more page. Okay. So okay. So let's add one more page. Yeah. So let's add one more page here. Why I cannot? Oh, that's yeah. I cannot really delete this. So anyway, so Markov process, Markov chain or Markov process in general. So you know, right? So you probably when you learn like physics. So let's say, so we have for you want to describe the evolution of a particle, right? So let's say evolution of a particle. Let's just think this evolution of particle of a free particle, right? So those particle is is like totally free. So there's no anything, there's no any force, a free particle. So those particle has two quantities, right? Position and velocity, right? Position and velocity, right? Position and velocity. So let's say, right? So this is the trajectory of the particle, right? So this is xt in R3, right? This is the trajectory of the particle. So it's a free particle, right? So if we want, if we, so this is not really true, right? If it's a free particle, right? So there's no force at all, right? It should be just, so either stop there, right? Or just keep moving, right? Using a uniform, using a fixed velocity. So the problem is, right, if you just study, right, if you just give you the state dt, right, if you just consider those state, so this is not a Markov process, right? This is not a Markov process, or not Markov process. But so why, right? Because if you just know the point at xt, right, you don't know the velocity, right? You cannot predict the future, right? So, but if you put the both velocity and both position and velocity, right? So then this is Markov process. This is a Markov process, right? Why, right? Because if you know the position and time t, and also you know the position and the velocity and time t, right? So you can predict the future, right? So in general, right? In general, right? So you, of course, you don't know those SDE, right? But I can tell you, right? This is a famous Langevin dynamics. Right. So if we write the position, right, like this, if we write the position is given by SDE, like DWT, right? This is Brownian motion. So of course, right? So of course, you will see this later, right? So xt, so given time t, right? This is a Markov process. Right, this is Markov process. And there's another one, right? This is called first order system. There's another one, right? So let's say dxt, right, equals to vt dt. So this is just the change of position equals to velocity. And also dvt, right, equals to, let's say there's some potential dt, then plus some drift term. So so this dynamics actually describe a particle moving in a potential, right? Moving in a let's say gravitational field, right? So this is the gradient field. So if you just look at xt, if you just look at xt solving this SDE, so this is not a Markov process or Markov chain. So if it's finite, this is not, right? But if you put the state space as in phase space, right? So this is called phase space. So in phase space state. So not just in physical space, but also in the velocity space, right? So t bigger than 0. So then, so it is a Markov process. Right? So actually Markov chain, Markov process is like everywhere. It's a basic, it's very basic notion, right? So this is a very basic notion. I mean, definitely much more general than martingale, right? Definitely much general than martingale. Okay. So this is a remark on the Markov property. In last lecture, I give you several examples. I will skip that. I will skip that now. But as I said, right, this is a basic notion. In general, right? So if you have, you can, in general, right? So usually the dynamic system, right, deterministic system or stochastic system actually are both Markov chain, right? Usually we want to model something. You want to model something, so you want this process is Markov. So Markov means, right, you don't need to consider the history, right? You don't need to trace a lot, right? So if a process is a Markov chain, Markov process, right? So to predict the future, right? To predict the future, you only need to start from the current state, right? So you can predict the future. But actually, right, currently there are some people doing work, right, considering non-Markovian process. So sometimes the history or memory effects, right? But that's a very recent things, right? And it's not like mainstream, right? So people want to modeling, right, using Markov process or Markov chain. Okay, so this is a remark. So last time I gave you several examples, so I won't talk anymore. And there are more examples in the textbook and in the exercise there, right? Okay, so let me make some remark on the construction of Markov process, right? So if you just read that, you might feel weird, but so I still suggest you to read that, follow the textbook, right? It doesn't tell you a lot, right? But basically, if you go through them, you can know, right, how to do those things rigorously, right? But most of the time, if you're doing research, maybe that won't help a lot. I will tell you, right, what essentially they did. Okay, so what we did here, right, is okay. So starting from a variable, we're starting from some variable space. Right? We're starting from some variable space, which is so this is S, right? Uh, so this is S, the state space, right? This is state space, and this is the sigma field of this S on this state space, right? And so let's say a priori we have a transition probability P. So this transition probability P, right, has two variables, right? So the first variable X. So this X is in S. So this A is a set, right? It's a set, right? So which is in S. So in this S. Okay. So if you fix X, if you fix this X, right? So then the transition density, right? Transition probability becomes a probability mirror, right? So if you fix A, right? You fix this, fix this argument, right? Then so the probability, transition probability is just a measurable function with X, right? So there's nothing magical here, right? There's nothing magical here. So this P, so this transition probability, right? This transition probability is just a matrix, a transition matrix. So possibly in infinite dimension. So let me give you an example, right? Finite dimension example. Yeah, let's just add a page here. Okay. Okay, let's just add a page here. Uh, so, okay, let's consider the example, right? So used by Scott Sheffield. So let's say we have two sets, right? So let's say this is set 0, set 1, right? So this state space is just 0, 1. Okay. So 0 probably means it's raining. So 1 means the weather is sunny. It's sunny. I should use. Okay. Okay. So let's say the transition probability, right? So this is transition probability, right? If today is rainy, right? So there are half probability, right? Tomorrow will be raining, and half probability it will be sunny, right? If today is sunny, so then there are 0.2 probability it will be raining tomorrow, and it will be 0.8 possibility it will be sunny again, right, tomorrow, right? So, so what is the transition probability here, right? So this transition probability here, right? So it's right x s, right? It's x. So this is a finite step, right? So s, so it's just a 0, 1. It's just a 0, 1. Right? So here the transition. So we know the transition probability matrix. Maybe this, I mean, maybe that's slightly different in the terminology, but it's this, right? So what is the transition probability matrix, right? So here, right, there are two states, right? So you transit from 0 to 0, right? You transit from 0 to 1, right? 1 to 0, right? 1 to 1, right? So you write this out, right? It's just 0.5, 0.5, 0.2, 0.8, 0.8. Okay, so this is the transition probability, right? We know, right? So this is called stochastic matrix. So why is called a stochastic matrix? So because, right, so this is all positive, right? So for Pij, it's all non-negative. And if you sum up, so it's sum to 1, right? So this is sum to 1. So what's this, right? What's this, right? As I said, right, what's this? So this is just a P 0, 1, P0, right? If you fix the first argument x, or this is just x, and this is a probability density on S, right? Probability density, probability measure on S. So this is not the state space, right? It's the sigma field on state space, right? So it gives you the probability, right? But it's finite, right? So we just give probability to each state, right? That's fine, right? So again, right? This is the probability. This is transition probability, right? X equals to 1, and X on the S, right? So this is the probability measure on so this actually is all the set of S, right? Power set. So for finite, this is just a power set of S. Okay, right? So this is our definition, right? For finite, right? Finite state Markov chain. Finite state Markov chain. Okay. Okay. So any questions? So no questions. No questions. Okay. So I will keep going. Right. So this is our definition. This is our definition of transition probability. I will erase this. So this is I write last time, but I want to erase those. So in the textbook, right? So we kind of a priori define some finite dimensional transition probability. So then from that, we can extend those finite dimensional probability to like the sequence space. So this is the construction, right? It's like existence part of Markov process. Okay. So, but as first, first we define those. Let's define those Markov chain. So what this is our definition of Markov chain. So, and this Fn, right? So this Fn is definitely x0, x1 to xn, right? It's the information up to time n. So if we call, so if we have this property, we have the property star, so then we call xn Markov chain, right? So just to make a remark, right? So what's this? So this is conditional probability, which is a random variable. So if you conditioned to the information up to time n, right? So you just get p, so p x n b, right? So we know, right? So we know p is measurable, right? So p is measurable, and xn is fn measurable, right? So of course this is fn measurable, right? So this this is a measurable function. This is fn measurable, right? So this definition basically says, right, these two random variables are equal. These two random variables are equal. Okay, so in the textbook, right, it's just a definition, and you can check this definition agrees with the one for finite or countable set, countable state space case we showed you earlier. Okay. So in the textbook, we first construct the existence, right? So this is the construction. So this is the construction. So how to construct this, right? So actually, I can tell you, right? This is everything we have. So give you, right? So let's say we have a Markov chain. We don't have Markov chain yet, right? We want to construct a Markov chain. So here, right? So here, what we do is like, let's say I give you a transition probability measure P, right? So this is just called transition probability. It's not. It's have two arguments, right? If we have transition probability and initial measure, so we want to construct. So we want to construct a Markov chain. We want to construct a Markov chain, right? The following way, right? The following construction, right? Is kind of, I mean, the following construction gives you one possible choice of Markov chain. Right? How do we do that, right? So we just let's say we define. So this is a way, right? So we define the finite dimensional distribution. So here, by this formula, by the formula star, we define all finite dimension distribution. So given a transition probability P, and so then you can check, right? You can check this is this really makes sense, right? Why this makes sense, right? You can check some fine. So I just tells you, right, the meaning of this formula, right? So this basically means, right, x0 is in the set b0, right, etc., and xn is in the set bn, and we have transition probability p, right? So to compute the the joint probability, right? How to do that, right? So we just integrate over all B0, right? Over all B0, right? Against the initial probability, right? This is iterated. This is an iterated integral. This is iterated integral, right? So for all possible values, x0 in B0, right? So let's say, right, this is B0, right? So x0 is here, right? Definitely we should integrate with the density mu, right? The probability mu, initial measure. And we have a transition probability P, right? So, and this is x1. And x1 is in B1. X1 is in B1, right? And you can keep doing this, right? So this is x2, right? So this is xn, right? This is xn, right? So to compute all the probability, right? You just do the iterated integral, right? And this is a way, right? This actually is the way we did for finite Markov chain, state Markov chain. So you can check using the previous weather model, right? Just two state, raining or sunny. Okay, and so this is just for finite dimension, right? If you just if xn just you consider from 0 to let's say 100, right? This is actually enough, right? But usually we want, right, when we study Markov chain, let's say xn, right, when I study Markov chain xn, so usually we want to study the limit behavior, like asymptotic behavior as n goes to infinity. So like, do you have a stationary mirror or something like that, right? Stationary mirror or ergodicity, right? Mixing property, something like that, right? So usually we want, so this is actually an important regime, right? So if you want to consider like 100 or 1000 xn, right? Xn for n is very large, right? You need to do some asymptotic analysis, right? So we need to study not for fixed n, but for when n goes to infinity. We want to study the sequence space, right? So we want to study those sequence space. So those sequence space, right? So that's why, right, we need to use the Kolmogorov extension theory to extend, right? This is a finite dimensional mirror, right? This is finite dimensional mirror, right? We use Kolmogorov extension theory to extend the probability on those set, right? Those set. So this is the sequence space, right? So this is sequence space. So those are sequence space. And we can extend the previously defined P mu, right? P, right? This is a finite dimensional P. And we can construct a P mu. So such that the finite dimensional projection is just to give you the previously defined P, right? Previously defined P. And I mean, so now you can consider, P mu. So this P mu is like a mirror. So this is a mirror on path space. Or here we can say sequence space, because it's discrete time, which is just omega 0 f infinite, which is just s, right, to all the natural number, right? So all the natural number. So mu is a mirror on path space, right? So if you do the time slice, right? If you project to, let's say if you project to time n, right, you get the mirror of xn. You get the mirror on xn. Okay. So this is actually the, if you study stochastic process, right, this is the standard way, right? So yeah. Okay. Any questions? Okay, if no, so let's, okay. So here, right, so here x, so here this is just a notation. So PXA, right? So let's say A is a set in the limit sigma field, right? Um, so let's say, so this is P delta X. So initially, if you're starting from a Dirac mass X, right? Let's say, so this means X0 is exactly X, right? You're just starting from X. And we want to construct all the probability, right? All the probability. So for instance, right, initially you're starting from a raining day, right? It's fixed, right? Also, you can starting from some mixed state, right? So one half raining, right? One half sunny, right? So that's possible be mu, right? But you can starting from a deterministic initial state, right? So if you know everything, right? If you know, so if you know everything starting from X, right? If you know everything of the path space starting from X, right, we can just integrate with the weights. So we can get P mu A. So this actually is a very easy observation, right? So let's say if you're starting from X, right, you're starting from X, you get a path, right, you get a path, right? So with certain weights, right? So this is PX, right? And this is initial state, right? Initial state, you can starting from possible others, right? So you can starting from Y, right? So you can give width for the initial state, or let's call mu, right? Dx, right? So if you just integrate with the initial mirror, right, you get this. So you get this. So basically, this is just coming from the linear property. Just from the linear property of star. So when I say star, it's just this. It's just this definition. Just this definition. Just this definition. Okay. Just this finite dimensional mirror definition. Right? It looks very, very ugly now, but okay. Any questions? Oh no. Okay. Okay. So if you construct the finite dimensional mirror like that, and using homomorphic extension theory to extend to the sequence or path space, so we can really check. We can really check this xn. We can really check this xn defined above is a Markov chain. So I mean, in the proof, I don't really show the proof. It's not I mean, it's just checking. But I can tell you, so this is nothing. So the proof is nothing, right? So it just, so all come from the definition, the star. I just showed you, right? Come from the definition of finite dimensional space. The definition of finite dimension probability. And then you just extend those to high to infinite dimension. Okay, so yeah, go ahead.
The P mu should be on sequence space, but here the left-hand side P mu is only on xn plus 1. Is it omitting that xn plus 2 is in the entire space? Xn plus 3 is in the entire space.
Excuse me, I don't understand. Can you repeat a little bit?
P mu is defined on the sequence space, x1, x2, xn plus 1, xn plus 2. But here there's only xn plus 1 belongs to B. Is it omitting that xn plus 2 is in the entire space, xn plus 3 is in the entire space?
I don't understand. What do you mean entire space?
I just mean that P mu should be on the entire sequence, but here there's only...
yeah, you're right. You mean this, right? Yeah. So this is a probability measure on like entire sequence, right? You are right. But for instance, right, it's a valid notion if we just write, so if we just write p mu, right? Let's say x0 from between A. Right? This is a well-defined notion. So this means, right? So this actually means, right? You project p mu to the first coordinate. So
Okay.
if you write this notion, this just means initial A. Yeah.
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 And if we want to prove this theorem, the left-hand side is the conditional expectation, and we prove this theorem by checking the definition of conditional expectation, right?
Yeah, you're right. So
Okay, and
yeah.
okay.
So we need, yeah, if you read the proof, so let me find the proof first. Right? So if you need to find the proof, right? If you want to go through the proof, right? You kind of, right? So this is Fn, right? So you need to choose some set, right? So this set is just the building blocks for the Xn. So we just choose the Xn, let's say in Bn. So we choose this A. And in the end, we show, right? So if, okay, how to show that? So
If we want, when we are checking the definition of conditional expectation, if we only choose if the integral satisfy for all A, it's not enough, right?
yeah, it's not enough, but this actually, so then for, so then why this is almost enough, right? Because this is like generating, right? So all we can show for all this kind of A, if you integrate this set, we integrate this set, so we actually get this. We actually get this. So this means, right, this is not enough, right? You are right, right? If you just check this condition, right, this is not enough. But we can use in like the extension theory, right, called Jenkins pi lambda system, right? Again, right? So we just use pi. So maybe just, so we can use in Jenkins pi lambda theory. So this system, right? This system is pi system. This is a pi system. This is a pi system. Why this is a pi system? Because if you take a, so this is A, right? If you take another A tilde, so you can A intersect A tilde is also there, right?
Yes.
Also there. And also, so we can show, right? So since, so this is the equivalent, right? So this condition satisfied. So we write all the set A such that this equality is true. And this is an integral equivalent, right? Equivalent. So,
It's a lambda system.
so this is a lambda system, right? Because integral, right? So this is a lambda system. And this lambda system contains this type of cubes, right? This type of cubes. So it contains all the sigma field generating about these cubes, right? So it can, this contains all set in Fn. Yeah, yeah, that's it. But the basic part, right? So I can tell you, right, from my understanding. So the checking is trivial. It's basically just trivial. So all the information, so all the information of Markov property is just here, is just here. So this is the key. This is the key for everything. This is the key. Yeah. So maybe I write somewhere. Yeah. So this is a key. We should be. So this is a definition, which really gives you everything you need, right? All others is like a theoretical checking. So right? So this iterative integral actually gives you all, right? Yeah. So this iterative integral is a mu dx0 p1 px0 right dx1 etc. So this is should be n right from xn minus 1 dxn. So this gives you everything. All others is just simply checking this, right, using some limit integral to limit theory. So, but this is the key, right? This is the key. Yeah, this is the key. Okay.
Okay.
Yeah. You can. So I would suggest all of you, right? So to you can watch some lecture videos I posted on yesterday's announcement and get some intuitive idea. And if you go back to check this, probably easier, because our textbook is very abstract, right? But I still think it's good, right? If we follow this book because so you want to talk to expert in probability, right? They all like this. Right? This is like their common language. So you want to do probability or related field. This is like common language we should know, right? Definitely harder than ungraded Markov chain, right? But it's worth to take the effort, right? Okay. Right. So the previous definition, right? If you use Markov, the Kolmogorov extension theory, we just get one concrete. We just get one concrete Markov chain, right? Yeah. So the following is is another characterization by Markov property, right? As I said, right. So this is another characterization, another form of Markov property. Right. So this is the original form. Right? This is the original form. So we just write this as a set, right? This as a set, right? You can check, right? You can check. So if here f is given by an indicator function of b, right? Of b, so then let's say this is so then definition, right? Let's call this definition. Then definition gives you the characterization star, right? Give you star here, right? And you can show this rigorously, right? So f here, as long as f is bounded, is fine. As long as f is bounded and measurable, f is measurable. So as long as f is bounded and measurable, we have this formula, right? So this actually makes perfect sense, right? If you conditional to the information and n time, right? So everything matters is xn, right? So xn is a random variable, right? We just fix this random variable and integrate all possible choices for y, right? So this actually is integrated on S, the whole set S. So it's a generalization, right? It's another form of the definition. Right? These two are equivalent. You can prove this, right, using the following monotone class theory, right? You can read that, but it's really a good application of Dawkins' pi lambda theory. So I will skip this. Okay. Okay. So what we want to say here, right, is this. So actually, is this formula. So this formula shows what, right? You can check this formula, right? This formula shows, so if Xn is a Markov chain, right? If Xn is a Markov chain, so then the finite dimensional, so what this shows, right? So what the development from here, what's the development from here shows, right? So the development from here showed the following. So if So if a priori, let's say if Xn is a Markov chain, so this is a theory in the textbook probably. So if Xn is a Markov chain, so then the finite dimensional space, then the finite, then the finite dimensional distribution. So finite dimensional distribution is band word. Distribution is given by the star, right? So the star I write here, right, is just given by this definition, this again, right? This star, right? So this finite dimensional definition is just given by this. So that's it, right? Everything is here, right? Everything is here, right? So we use the transition probability, right, and write the probability, a finite dimension probability using iterated integral, right? You have a Markov chain. You have a Markov chain, and that's give you all the information, right? That's give you all the information. Okay. And this formula, right? And this formula is very useful, right? I just you can prove this. Okay. So to sum up, right? So there are several ways to say Markov property, right? So this is the first way, right? Just the definition, just definition. And this is the second way, right? You can prove this from the definition, right? And we want to generalize this. We want to generalize. So this too, we want to generalize the Markov property. So this is what we showed in the end of last lecture, but it looks like we go this again. Okay, but that's fine. So let's say, so this is a Markov property, right? This is y, right? Omega 0 to r is bounded and measurable, right? It's just a random variable. And if you shift a little bit, right, to condition to FM, right, you just get this random variable. So the random variable of this, all the randomness come from XM, right? So what this really means, right? This really means, right? We first take the expectation, right, of y. So starting from x. So this is starting from x, right? So which means the initial measure, right? Initial measure is just delta x here, right? Just delta x here. Okay. And then, right, so all the randomness I said, right, is come here, right? So you first take phi x, right? Then you evaluate and xn, right? So this makes sense, right? This makes sense. Let's, for instance, right, why this makes sense? Why this sense? Why this makes sense? Right? Why this makes sense? So you can think in the following way, right? You can think in the following way. So let's choose y. Let's choose y is a random variable, right? It's a random variable from omega 0 to r, right? Which is bounded, and bounded, y is bounded. So for instance, we can choose y omega, right, is on the sequence space, which depends on all the coordinate, omega 0, omega 1, omega 2, etc. Right? So y, so now if you m, right, so this is a shift, right, theta m is a shift. So if you do the shift first, right, what do you get, right? So you get omega m, right, shift to the left times, right? So omega m plus 1, m plus 1, etc., right, etc. So in this particular choice, for this particular choice, what we have, right? The theory tells us, right? Theory tells us. So we do the conditional expectation, right? But now is this is really xm, right? So this is really xm plus 1, and we condition on fm, right? So the theory basically tells us the following, right? So e x y. So y also, right? So here is omega 0, omega 1, right, etc. Right? So this is a quantity, right? This is a function, depends on x. But now we write x equals to xm, right? So this is the Markov property. Right? This is the Markov property. Right, this definitely makes sense, right? This definitely makes sense, right? So if you conditional on fm, right, all the past doesn't matter. Right? If you conditional on fm, so only this matters, right? Only this matters, right? So that's why all the randomness just come from to xm. Right? So it's again a direct check. So direct check to prove this, right? Prove the theory, we just direct check by the formula. By the formula we just mentioned, which is the application of the Markov property, right? So we use the following formula. The following formula: m equals to 0, fm xm. So mu dx0, right? f0 x0. Right? So then we do the transition x0 dx1 f1 x1. We do the iterative integral, right? Pn minus 1 xn minus 1 dxn fn xn. Right? So we just use this formula and checking this. I mean, not checking this, but checking the theory, right, directly. Just directly checking using the definition of conditional expectation. Conditional expectation. Okay. So this is just a remark, right? This is remark. So last time, right, in the last few minutes, right, it seems also last few minutes of this as well. So it's called the Chapman equation. So this equation is very useful. I mean, it's very useful when you want to derive some PD, right? Let's say the transition of some Kolmogorov forward equation or something. You will need this, right? So what does this theory says, right? What does this says? What does this say, right? So this says the following, right? If you're starting from x, right, and m plus 1 and z, right? So this initial point, and you're starting, it ends with z, right? So you can do decoupling, right? You can do the decoupling. So you just decouple, right? Decompose, right? Just decompose according. You just decompose according to the value of intermediate state, right? Of let's here is xm, right? So right, this makes perfect sense, right? This makes perfect sense, right? So I cannot really erase this because it's again. So from x to y, right, to z, right? We consider the intermediate state y, right? Y is a possible choice of xm, right? So there are many choices of xm, right? It can be here, it can be here, it can be here, right? So then we just consider the path first reach y, then going from y to z, right? But of course, right, there might be possible many choices from x to y, right? there might be also many choices from Y to Z, but that really doesn't matter. So here we really use is the, let's say, conditional on Y, right? So it's like the Markov property, right? It's the Markov property. So yeah. Yeah, so we can prove here, right? We can prove, we already mentioned the proof, right? We already mentioned the proof, right? So you can check this. So I will basically just skip those proof. Okay. Yeah. But this is very useful, right? It's very useful, right? So that, right, the idea is like given Y, right, two paths are independent, right? Given, let's say we have Y, right? So this path and this path are independent, right? So it I mean, looks like you can just time those probability, right? Like you take the product of those two probabilities. Okay. So when we want to consider large time behavior, right, recurrence and others, we need to consider stopping, right? So we need to consider stopping time. So we need to consider stopping times. So the Markov property can extend to shift with stopping time. So this is a theory called strong Markov property. So let's just briefly mention the shift. We don't have a lot of time. Maybe I just state the theory, and we prove this and cover recurrence and next lecture. Okay, so we just basically recall, right? If n is a stopping time, which means, right, so the level set is Fn variable, right? Is Fn variable. And we can define filtration, right? So this is not a filtration. So the information knowing, so this is the information knowing and time n, right? So this is the information knowing and time n. So which contains all the set A. So as long as you take the slice intersect with the n equals to small n, right? So which is Fn variable, right? So in particular, right, so you can see, right, so this is in Fn, right, and this is in Fn. Oh. For stopping time n, we can do the shift. So this is a random shift, right? This is a random shift. And you don't need really care about this, right? This is not important, right? You don't need really care about this. So we basically just define the random shift for the random stopping time, which is finite. Okay. So strong Markov property basically says, right? Right? So the previous property holds when you change the fixed number n to a stopping time, capital N, right? And also we can consider like a sequence of Yn. So N is a sequence. So a sequence of random variables, which is uniformly bounded, which is also uniformly bounded. And again, right, so this part is a conditional expectation, right? Part is a random variable, right, which is Fn variable, right? So this definitely is Fn variable. And so here, right, so what does this mean, right? What does this mean? This means you first choose X, you choose N, right? So it's a number, right? This is a number. So this number depends on X and N, right? This is a two variable real valued function. So then we evaluate this real valued function and this random variable Xn and a stopping time n. This is an integer. This is a random integer stopping time. This is a random variable. Okay. Basically, it's the same, right? So so this, as I said here, right? So all you have to do is break things according to the value of n. So we just break everything according to the value of n, and then we sum up, right? Okay. So the idea, right, is so this is true, right? This is the equivalent, right? This is the equality of two random variables. So to show these two random variables are equal on this set, right? So what you really need to show is the following, right? We choose any set, A, is arbitrary set, right? It's arbitrary set. And we just want to integrate, those sets on this. Okay. So if these are true, we are basically done, right? So those are just the properties of conditional expectation. So all you have to do is like, so this is integral, right? So this means integral, and we just write this integral, right, as the sum over the subsets, right, according to the value of the time. So then we can just so this is rewrite, right, from this step to this step is just rewrite using the definition of the conditional expectation, right? So conditional expectation, right, is something like this, right? dp, right, equals to a x dp. So if a is in f, right? So this is just the properties of conditional expectation, the definition of conditional expectation. And then from this step to here, right, we can use the previous Markov property, right? So then we are basically done. I will stop here. There's one question. So in the remark on page 3, y can take xm as its argument. Is xm a random variable or xm defines on x? Page 13. So this page. Maybe not.
No, the page you know.
Okay. Okay. So what do you mean? Y can take values? Okay. So y, okay. So y is a function, right? Y is a random variable. So y is from omega 0 to r, right? Right. So y is not.
Yes, but on the left-hand side, it is y of xm.
Here.
No, on the left-hand side.
Here. Yeah. So here just the arguments, right? Yeah, definitely, right? So it's like we write a function f, right? It's like we write a function f, right? We can define this, right? This is real value. Right? So this is a random variable, right? So this is a random variable, right?
Yeah, but xm is a random variable, so it takes it maps from the state space to a real number, but
yeah.
y takes. I mean, y maps from the omega 0 to r. So I don't know why.
Oh,
why
okay.
can compensate with xm?
Yeah, this is exactly the same, right? As you say, it's a random variable, right? So I mean, this is a random variable, right? But you can also call this function. So why? Because I mean, it's not a really a good name to call this random variable. Let's say if you give you a fixed realization, right? There's no randomness at all, right? So you get a number, right? But usually, right? So this is a coordinate, right? This is a random variable. So this is this, right? So in this sense, we write y omega, right? This omega is a random path, right? It's a random path. So in this case, right, this whole thing is a random variable. But if you just say y, right, you can just call it a function. right? It's like f xn, right? So this is a random variable, but you can just say x is r to r, right?
Yeah, but I mean, y is not r to r. Y is from omega 0 to r. So you assume omega 0 is r
so
to n.
why? So because y is defined on the sequence space, right? So omega zero is s. So it's s to n, right? So it's a sequence space. So it is like omega 0, right? Yeah. So this is yeah. It's not a really you can call it a random variable, right? You can call this function. Yeah, because the domain is just Sn, right? Sn is yeah, it's very hard to explain, but it really matters, right? I can tell you this is not a problem. Yeah, you can think, you can double think that, right? It's just a name, right? Just a name. So for instance, so all the randomness of y coming from this path, right? This path, not by y itself. So y is kind of indicator, right? If you see some examples, so y in most applications is some kind of indicator of certain events, right? Of certain events. Right? So y is kind of indicator function of certain events, right? Definitely, right? This so y if you just for a fixed trajectory is I mean there's no randomness, right? But usually y is composed with those things, right? So they have randomness, right? So sometimes maybe in the statement we call y a random variable, we don't call it a random variable, right? But you can call it a random variable. We just call it a bounded measurable function. Yeah. Did you assume omega 0 equals to not necessarily, right? So Jiao Zhang asked the question, do we need to assume omega 0 equals to r to no, not necessarily, right? So S can be very general things, right? S can be n, right? For instance, right? S can be like 0, 1 finite space, right? Of course, so S can be R, right? S can be R, right? It can be more general. Yeah. So any other questions? You have I will just stop, right? So you have questions I can answer. So but otherwise yeah, so yeah, but otherwise that's it. Okay, I will stop sharing. So any questions? If no, I will end. So from next lecture, I will talk about recurrence. Yeah. So I might skip the notes below. I might skip the notes below, but just to talk about this part, the recurrence part. So there are very interesting theory called the reflection principle, right? So we need the similar argument later in Brown motion. Right? You can read that, but I will skip that because we don't have time. Okay, so any questions? Otherwise, I will end all the meeting.